Right. I'd like to welcome everyone to the Sustainable Energy Seminar. This is a series put on by the Wisconsin Energy Institute, and it's also a class for the Engineering for Energy Sustainability Certificate, as well as the Masters in Sustainable Systems Engineering. We do this every other week as a live presentation, and our goal is to highlight the cutting edge research and expertise from across UW-Madison and beyond to showcase how different disciplines understand energy challenges and develop solutions. So throughout the semester, and you're welcome to join even if you're not in the class going forward, you'll hear different experts in science and engineering, social sciences and humanities to see how they view energy challenges and develop sustainable solutions. This seminar is open to the public as well. So if you're joining online, thanks for joining us, and make sure to register for all the upcoming seminars in the series. But you're also welcome to join us here at the Wisconsin Energy Institute. We do have live captioning available. I believe that feature is turned on. You just click on the live transcript button to toggle that feature. If you're joining us online, please use the Q&A box to ask questions of our speakers. I'll be monitoring that. And then if we have questions in the room, make sure our presenter repeats that for the online audience so everyone can hear. With that, I'll introduce our first speaker to kick things off and really provide a great high-level overview of some of our biggest sustainable energy challenges. So Dr. Tim Donohue is a professor of bacteriology, and he is also the director of the Wisconsin Energy Institute, which we're in, as well as the Great Lakes Bioenergy Research Center. Dr. Donohue is an internationally recognized expert on bio and genome-based conversion of renewable resources into valuable products. He is a past president of the American Society for Microbiology, and since 2007, he has served as the principal investigator and the director of Great Lakes Bioenergy, which is a U.S. Department of Energy Office of Science-funded Renewable Fuels and Chemicals Research Center. The center has trained some 1,000 scientists and engineers, made advances contained in over 200 patent applications and 100 licensed technologies, and provided the scientific knowledge and that has formed the basis of 5 startup companies. Excuse me. Today, he'll be giving a high-level talk on the grand societal challenge of developing sustainable and cost-effective fuels, chemicals, and materials from renewable resources and using bio-based methods. So welcome, Tim.
Thank you. Thank you, Scott. Can everyone hear me? Can they hear me online? Scott? Yes, yes? Before I get started? I can hear you. All right, great. So it's really a pleasure for me to be here today, both because this is something we haven't done in a while, and because I'm really honored that Scott asked me as director to kick off this series for the semester. So as he said, I'm going to try and do 2 or 3 things today. First, for those of you who are new online to the Wisconsin Energy Institute or in the room, I'm going to take a minute or 2 to tell you what the Wisconsin Energy Institute is. And then I'm going to spend most of my time in 2 sections. First, framing what I call a societal grand challenge or opportunity, depending on whether how you look at the world, and renewable energy technologies, and then talk about some of the bio-based activities that are going on within WEI and elsewhere around the US to help us meet that challenge or take advantage of the opportunity. So first, what is the Wisconsin Energy Institute? Its tagline is it's a catalyst for the UW-Madison campus to move forward in energy. It has programs in stationary energy, energy capture, storage, and distribution, in transportation, fuels, vehicles, and engines, and in products, chemicals, and materials. And we also collaborate as a cross-campus center with experts in policy, economic, and societal impact so that our innovation can do good for the public in the spirit of the Wisconsin idea. We'll come back to that again in a moment. So let me now move on and talk a little bit at a high level about the energy situation in the US. But what I'm about to say at the US, by and large, would map around the globe. There are differences between developed and less developed countries. But the point that I'm going to make, the points that I'm going to make on the first couple of slides here would be generally true if you look globally as well. So on the left-hand side of the slide, you can see where the United States has been gathering its energy from, going all the way back to its inception in 1776. And you'll see early on, there was green energy, and that's because most of the energy we got was coming either from burning wood or from hydropower, dams on water collection on rivers and whatnot. And then in the mid 1800s, you started to see fossil fuel come in as a major energy source and overtake that, to the point now where in 2022, 79% of the energy that the country uses comes from a combination of petroleum, gas, and coal. And depending on how you think about that, that's a large fraction of the total, but it's actually the lowest percent fossil fuel use in 100 years. So the numbers are going down, even though fossil fuels are still the big elephant in the room. And the other way of looking at that is if you take this data and replot it on a percentage basis, and you'll see early on, wood was the big elephant in the room, and now fossil fuel-based energy is the major source, with about 21% coming from the non-fossil or renewable sector. And that's a combination of nuclear, wind, biofuels, hydro, and all other renewables, including burning wood, which was the major source back here. You can see there's some shift in these numbers, but the government's own projections are that by 2040, if you take this out 20 years to the right, this blue part of the graph is still going to be 76% of the total. So if we think we're running a race to capture more energy in the country from a renewable standpoint, that race is more like a long distance event, like the Ironman that ran past the building yesterday. It's not a 100-yard dash. It's going to take us time to get there, not because these renewables aren't coming up, but because you see we have an ever-increasing demand for energy in the country. So we're moving into strong headwinds as we try to come up with other technologies. So what is all that fossil fuels used for? So it's used as a source of both heat and electricity, but also it's used as a source of fuels and many other chemicals. And those fuels include automotive, diesel, aviation, small engines, marine, lawnmowers, other types of small engines. And it's used for thousands of chemical products that society depends on. Lubricants, plastic, clothing, medicinals, I could go on and on. So think about that in a pictorial version. I've stolen this picture from a DOE report, and it lays out a typical barrel of oil and what it's used for. And you can see about 75% of the volume of that barrel is used for transportation fuels. And about 15% of it is used for chemicals. On the left, it shows that fraction that's used for fuels is half of the profits that come out of that barrel, whereas the small fraction that comes from chemicals is half of the profits. So although we don't often think about it as we drive by a gas station every day, fuels are the large volume, low value per unit product of a barrel of oil. It's chemicals that are the small volume but high cost per unit that drives the petrochemical industry. So I want you to think about that as we think about what we can do with this challenge or opportunity in biology moving forward. Summed up, this is a multi-trillion-dollar per year industry. If you think about the petrochemical industry, just in the United States alone. And if you amortize that over the globe, it gets even larger. So with that as a backdrop, we also know there are numerous calls for diversifying the energy sector around the globe. And I'm going to go through a couple of the arguments or logic points that are made to call for diversification. The first is that fossil fuels are a major greenhouse gas source. On the left here, it shows that in the US, in 2022, I think this data is from, we generated almost 5 billion metric tons of carbon dioxide from the use of fossil fuels, petroleum, natural gas, and coal. And that carbon dioxide is the major greenhouse gas that's produced in the US. Over 80% of it, of the greenhouse gases, come from CO2. And of that, with that CO2 that's produced, the planet absorbs most of it. About a third of it goes into the ocean, causing a change in pH and changing in that ecosystem. Only about a quarter of it is reassimilated by plants on the land of the ground to give us, to support plant growth. The remaining 45% of that CO2 is absorbed into the atmosphere, changing the atmosphere that we breathe every day. So here's one set of reasons why people are calling for a change in the diversification of the energy systems. Another reason for the call is thinking about natural disasters. So here's some examples from 2 years ago where Hurricane Ida plowed right into the Gulf Coast. And as a consequence, it created a huge problem for people who live there. Power outages, gasoline shortages because the petrochemical refineries went off the grid. And this then becomes true all over the United States. We don't have a resilient system to deal with natural disasters. Last year, I will say we were fortunate that we didn't have too many natural disasters hitting the United States. And I say that even though my in-laws' house in Fort Myers, Florida got destroyed by Hurricane Ian. And so far, we haven't had a similar situation to what we had in 21. But for those of us who have been around for a couple of years, you've seen me use other versions of the slides with Hurricane Sandy and whatnot going up the East Coast. So there's a need to be able to be resilient to natural disasters and be able to generate backup systems. Backup systems could work something like this. So let's take as an example what happened when there was a major change in the electrical system due to solar eclipse back in 2017. That was correctly predicted, by the way, by scientists in 1932. So anyone who says we can't predict the future, here's a sign that we can. So on that day, if you were watching what used to be called Twitter, you would see statements like this, that this eclipse is going to test grid reliability in response to a major change in solar panel capabilities. So here's an example of the state of California monitoring how much electricity was being generated on the day of the solar eclipse. And there was none until the sun came up. Sun came up, systems went online, solar eclipse hit here, boom. Depending on how many solar panels in the state were hit, it went down, the eclipse was over, and the system came back on. So here is a system that was resilient. When the solar panels went down, nobody in the state of California lost electricity because there was other systems that kicked in. to handle the loss in solar power. And as soon as the light came back on, the solar panels came back on and the systems work. Contrast that with the example on the previous slide. A natural disaster, but the system works. Wouldn't it be better if we had resilient systems like that all over the country and the world in the future? So here's another example. Again, these are not my data points. This is federal reports I'm showing. This shows every state in the United States. And on the bottom, it color codes how much energy they produce and how much energy they consume. And you can see there are some states that are large producers and large consumers. And then other states like Wisconsin, where at least most of us live, that are large consumers but produce very little. So from this in 2021, you can see that energy distribution is asymmetric. There are large producers and large consumers, but then small producers and large consumers. And there is supply chain insecurity. Again, the natural disaster hits here, the whole country is affected because most of these states are not able to produce. And that leads to socioeconomic inequality as well, because people up here who could produce energy aren't, and they're not benefiting from the activity to do that. So in diversifying, can we get to a place where the color coding is more equivalent across the states and across regions within a state that allow us to be good shepherds, do it well, but consume what we need? So now let me shift and say, now let me shift and move on to the major part of what I want to say, and that is to talk about biology's place in creating a new energy future. So it may seem odd, but before I get into examples, let me just say that I don't want to sound like I'm a snake oil salesman here, giving you my view of reality. What I'm about to say is based on federal and private sector experts' reports. And here's one of my favorite quotes, which basically comes from this McKinsey report called The Biorevolution, where they estimate that up to 60% of the inputs of the global economy could, in principle, be produced biologically in the future. Not today, but in the future. And here's some other reports. All of these slides are available online that you can go and click on these. Either government reports that actually, although they come from the White House, they've been supported by both parties, as well as other private sector reports. So what do I mean by a bio-based economy? So if you think about where we are today, we have industries that create a lot of bio-based technology, use agriculture, biotech, fuels and chemicals, ethanol, or biodiesel from soybean oil or algal oil, and the forest industry, pulp and paper products, as well as wood products. Over here, we want to get to a place where there are bio-based substitutes for things that come from petroleum, as well as new products that come from abundant residues that I'm going to talk about. And that includes commodity chemicals, plastics, polymers, materials, fuels, renewable natural gas, consumer products, including makeups and other personal products, dairy, food, beverage, pharmaceutical, and medicines. And we're poised at a very interesting time to move from here to here, given the ability of cross-disciplinary new technologies to get us there. Included in this are bio-based things like genomics and synthetic biology that has the ability to make designer molecules the ability to do that in an automated way so that machines can help us do things faster than people. It also includes traditional techniques using bio-based materials like catalysis, hydrogenation, and electrochemistry, either on their own or what I would call hybrid technologies, where biology takes a molecule so far and these approaches polish it or bring it to market. And it includes the ability to take advantage of high performance computing and artificial intelligence and machine learning. And I'll give you some examples of those. So for those of you in the room who are students and young people, I wish I was your age, because you're really sitting at a very critical inflection point in society where we can really think about bringing all of these tools to bear to create all of these things from bio-based materials. So if this was a course called Bioeconomy 101, again, to say it a different way, there's a future that looks for renewable sources of heat, current, and natural gas, transportation fuels, the hydrocarbon fraction of aviation, shipping, naval, and autos. Ethanol you might think of, but in fact, that's a minor player in my view as I think about this today, because it only works in gasoline. And a variety of consumer and industrial chemicals, polymers, and materials. Some of these technologies are nascent. Some of them are further along. So renewable natural gas is further along than sustainable aviation fuels that I'll talk about in a few minutes. But the research that's going on campus in the Energy Institute can help us get to market even better any of these technologies that you want to talk about as I give some examples. So how do I think we're going to be able to meet our growing needs for food, energy, chemicals, and materials? And the way I, in these reports, lay it out is that we have the ability to make all of the materials over here from abundant non-food, so-called agro-industrial residues. So things that come from animal or plant material, things that come from industrial or municipal byproducts that are currently residues, and things that come from carbon dioxide that will continue to be emitted into the atmosphere by existing human and industrial activity. So all of these materials on the left and down here should be thought about as raw materials that can go into a refinery and be converted into these products. That refinery could be a biorefinery with microbes in there, for example, converting those products. But that refinery could also be a more chemical refinery that's fed with bio-based raw materials and makes those products. I'm agnostic to that, although I am a microbiologist. I have my bias for what microbes can do to be in there. But if we generate those types of refineries and site them all over the country, we'll have an industry that's sustainable with a better carbon footprint, agile and resilient to change, and able to produce products locally where those raw materials are generated. And I'll talk about that a little more when we come back. So you may think I'm crazy to think that we have enough residues to make a dent in our energy grid. So here's a map of the United States, and it's a heat map. It's color-coded by county to show where we have hotspots that produce a lot of ag residue, either from current farming activity or from just natural perennial growth of trees and crops or industrial activity. And if you map that out, you can see that we can generate billions of gallons of fuel from those ag residues if you look across the United States. Whether that's material that's currently in landfills that could be bioconverted to wastewater, animal manure, or other organic waste. So we are, if you will, the Middle East of ag residues in this country, and we should be able to convert that into products instead of depending on foreign sources of that material. So again, the way I think of a renewable future is it needs to be diverse and include many different types of technologies. Clearly, there's going to be solar and wind. There's going to be hydro. But what I'm going to shift gears a little bit now and talk about is the use of these agricultural residues in a refinery to make fuels and chemicals. And the first reason for doing that is that we're making fuels and chemicals from plants that normally remove CO2 from the atmosphere instead of making it from fossil fuels, which when used as a source of fuels and chemicals, releases CO2 to the atmosphere. So this could be a net greenhouse gas benefit to society. So this is not a new idea. And in fact, back in 2006, we were proud on the UW-Madison campus to be part of a group that helped the US Department of Energy write this report, calling for research to break the biological barriers to produce ethanol from non-food biomass, so-called cellulose. The country at that time produced over 1 billion tons of lignocellulosic biomass every year. If you look at agricultural activity, crop growth, forestry, and other acreage, native prairies or land that's not used for anything, is called for the creation, this report called for the creation of large research enterprises to generate the knowledge to break those barriers. And in 2007, the Bush administration and Congress authorized the formation of bioenergy research centers in a separate program. And in 2016, those centers were refunded for 10 more years to remove the biological barriers now to use non-food so-called energy plants, and I'll explain what those are in a moment, as feedstocks, and to produce, instead of ethanol, hydrocarbon fuels and chemicals. Okay? So this is now a long-standing program that's received bipartisan support in the United States government, starting with the Bush administration through the Obama, Trump, and now Biden administrations. And it's been very successful, if I can say that without seeming selfish. So the goal of these centers was to generate the knowledge to create fuels and chemicals from lignocellulosic biomass. Notice that's a tree and that looks like grasses. It's not corn. It's not soybean. It's not a food crop. And given the 1 billion tons of biomass that are on the land, it was estimated that if we could convert just half of that material into fuels and chemicals, on the fuel side, we'd be able to replace 30% of the petroleum products with lignocellulosic biomass derived fuels and chemicals. So that's why we've drawn one out of these 3 barrels as green and the other 2 as black, denoting they come from fossil fuels. And we now know from looking at the cropping systems I'm going to talk about, these so-called energy crops, if it's done right, the greenhouse gas footprint of this activity would be 3 to 5-fold lower than producing them from fossil fuels. And this would provide us with the hydrocarbons for all of those engines, chemical substitutes, And I'll be a little aggressive and say, even some things that the petrochemical industry can't make today, because microbes have been doing chemistry longer than people, and we think we can make products in microbes that people haven't been able to figure out how to make in a petrochemical refinery. So that's where I'm now going to spend a few minutes talking about Great Lakes Bioenergy, because this was one of the original centers that was funded by DOE to now convert energy crops into fuels and chemicals. So first question you might ask is, how are we going to do this? So what I want to introduce is the concept that the ability to take these bioenergy crops all the way to product has a huge issue up here in the front end that I'm going to define as developing precision agriculture. You've heard about precision medicine. They use genomics to figure out how to treat people with the right drug when they have a specific version of a disease. So we have been looking across the north central region of the US for land that's available and productive to grow crops. And this map here on a county-wide basis, again, is a heat map. These clear colonies are some of the less productive acres in terms of ton per acre. These dark green ones are the more productive acres. And you might say, well, that doesn't make sense, because this is where these yellow counties are where we grow crops for food. And you're right. Food production is a low productivity per area enterprise, whereas the land that's not suitable for growing food is very productive. It's just not corn and soybeans. It's switchgrass, it's trees, it's native prairies that can be responsibly harvested to be used as a feedstock to make fuels and chemicals. So we look very carefully for acres that are productive, that are good hosts for perennials. Perennials are crops that come back every year. Crops that come back every year do that because they have deep roots and they don't need specialized agricultural systems to grow. In my backyard, they're called weeds. They don't need fertilizer. They don't need pesticides. They're also typically polycultures because no weeds ever grow by themselves. There's typically multi-species in there. So they're very good hosts for polycultures. And critical is where we place these. So why did I draw these circles? There's about 4 dozen of them in the north central region. If you look if you were to look at these circles, I would argue you could place a biorefinery in the middle of each one of these circles and transmit enough biomass to that refinery to produce tens of millions of gallons of fuel every year. Why is that important? Because you don't want to take crops from here and ship it to Louisiana to process, because the shipping cost will kill you on an economic and environmental basis. So all of these are sites where farmers who produce those crops could pass it off to refineries and buy materials and make money for the local rural community, bringing into this industry communities and jobs all over this region. So this has a large amount of both environmental and socioeconomic benefits. We've now done this at a much higher grain scale. If we look at 30 by 30 meter plots across the north central region, we can actually find subregions within areas that are currently used to grow corn that are just not as productive as other regions. And maybe Farmer Jones should think about practices that move from what the family's been doing for decades to new practices, and they might have a better economic, environmental benefit by doing that. And we've now done this over the whole of the United States. We have a bioenergy crop atlas out there for the whole United States. So what do we see as crops? None of these are things you get to eat. Poplar trees, there's some poplar out in front of the building. Switchgrass, which is this one, and sorghum, which is this one, and mixed species, as I said. So we are also utilizing on the feedstock improvement and precision genome-informed improvements to these crops so that they're more productive, higher yield per acre, and the chemical composition is modified in a way so that when we make juices out of them, they have higher value for downstream conversion into fuels and products. A large fraction of what gives us productive crops is stuff that we never see. The interactions underground between the plant, the microbe, and the soil geochemistry. So we're investing a lot of time in understanding what that is, how it varies across the state of Wisconsin, across the state of Michigan, between Michigan, Wisconsin, North Dakota, et cetera, to advise farmers on how to improve the quantity and quality of the feedstock they would get, especially in response to year variation in rain, in temperature. And I can tell you, if you do this over 15 years, no two crops are the same every 2 years when you harvest them. So there are big differences that we've seen. So if we're successful at all of this, here's one reason why it will lower the net carbon emissions from greenhouse gases. So here's a graph that's actually in this IPCC report that talks about ways that we can prevent the increase in global temperature from industrial and human activity. And one of the big drivers is how do we drop the global CO2 emissions? And every one of their models that get us to a 1.5% reduction in global temperature depends on significant change in agricultural activity. In other words, they rely on climate smart or precision practices that lower greenhouse gas emissions by decreasing the use of fertilizer. Again, perennials don't need fertilizer. Pesticides, the amount of fuel that it takes to do modern agriculture, just the tractor use, and the spreading of pesticides and fertilizer, the amount of lime to adjust the pH, favoring higher carbon and nitrogen sequestration by crops, forestry, and other land use. That's the AFOLU piece. And promoting bioenergy carbon capture and storage underground. Perennials have as much carbon underground in their root system as they do above ground when you harvest them. So the more acres you grow in perennials gives you carbon to turn into fuels and chemicals, but it also sequesters that carbon under the ground for you. Another major part of this is cost-effective, feedstock agnostic deconstruction to get the bioenergy crops into its major fractions, which are sugars and aromatics, and then use genomics to mitigate the impact of crop, soil, and weather on downstream processes and engineer industry-ready microbes to convert these in a fermenter into products. So let me give you a couple examples of that last statement. So let's consider for a moment the sugars that we would get from the cellulosic polysaccharide. That's about 60% of a ton of biomass that would show up at the refinery gate. We are focused on making isobutanol out of that. Isobutanol is a 4 carbon alcohol instead of ethanol. excuse me, a 4-carbon alcohol instead of ethanol. And it's already been approved by the EPA as a sustainable aviation fuel. If you read the newspapers, you'll hear about sustainable aviation fuel as an additive up to a certain percentage. It's a blend. It's also being passed off to chemical engineers in what I would call a hybrid technology, where they will polymerize that into hydrocarbons that have properties that mimic the hydrocarbons that come out of petroleum. So it can actually be used to replace the hydrocarbons in diesel engines and in sustainable aviation fuels. Although we can make it and we can model how well we're doing in a computer, we know we have bottlenecks in producing it at rate, tighter, and yield in order to make it at the cost that industry is going to need to build a refinery, to roll this out, to make enough to meet the demand, the billions of gallons a year that the commercial aviation industry in the United States would need. So what about the rest of the biomass? So this is about 60%. It's 30%. These are aromatics. For those of you who aren't chemists in the room, you've probably heard of xylene and benzene and toluene that are solvents that come from fossil fuels. Those are also, or phenol, those are also the precursors for a large number of chemicals that our petrochemical industry makes. It turns out this lignin is composed of polymer units of these aromatics, and chemists in the center have helped us get at these aromatics in a form that we can feed to special microbes that have an appetite for these compounds and are able to convert them into aromatics that, again, the aviation industry needs as an additive to run their engines. The aviation industry does not want to hear me tell them, here's a new fuel and here's a new platform, and you go change every jet engine on all of your planes and you can make a lot of money. What they want are molecules that will fit within the current engine performance system, right? So we have aromatics that would be able to be replacements for the aromatics that are in the fuels that they get from a gallon. They're also a source of large numbers of chemicals that can make things like lubricants, polyesters, nylons, biodegradable plastics, et cetera, et cetera. And again, we've modeled the economics of this. We know where the bottlenecks are, and we're now overcoming, making them at a rate, a tighter, and a yield to improve the economics so that the industry would deploy it. I'm almost done. I just want to shift gears and talk about one or two other examples that are now out of the energy crop realm. But some of you either may have grown up on a dairy farm or know people that grew up on a dairy farm in a state like Wisconsin. So there's another large agricultural residue industry in the state of Wisconsin, and that's called the dairy industry, who has now come to us and said, what can you do with our residues? And if you think about it, they can be used to decarbonize an economy as well. Across the country, you can think about the dairy industry being the host of a strategic dairy reserve. You occasionally hear about the president releasing gallons from the Strategic Petroleum Reserve to deal with a natural disaster or a war, so that the price of oil doesn't go up. Well, nationally, we produce 30 million metric tons of milk permeates and 2 million metric tons of whey just from making Greek yogurt every year. In Wisconsin, we're about 30 billion tons. And every time you make cheese or cheese, for example, you produce 9 pounds of whey for each pound of cheese that you make. So we are sitting on literally tons of dairy residue. So again, this is what the value of that dairy residue is today. We can take that and feed it to microbes and make different products, some of which either at current levels are as valuable or more valuable than the material we're feeding them. And if you were taking a microbiology course with me, I could convince you that there's a way to improve that yield by improving the metabolism of the microbes to get the bars as big as blue. So we're working on trying to valorize these residues for the dairy industry so that dairy farmers can make more money out of a ton of milk than they currently do today. We've talked about this enough that we've now had people donating residue to us to analyze, and we've done it with everything from the leftovers from our sugar fermentations, from starch ethanol fermentations, from cow manure after we solubilize it, to these milk permeates, to milk permeates that we mix with acid whey. And not surprisingly, these are different chemical compositions. The composition and fermentation conditions change the product profile, the yields, and the value of the fermentation products. But now that we've done this on a variety of different feedstocks across a variety of conditions, we can actually use machine learning to predict what microbes are common in each of these that help us make certain products, and what microbes are different in some of them that are responsible for the different product yields or spectrum of products that we see. Those are predictions. We now need to go into the lab and do experiments to test those, because it would allow us to improve the performance and the product yields of this to help the dairy industry do this at scale, because they're going to want a process that works every day, depending on what they can buy and how they want to mix it. Last example I'll give is to talk about something that we're always going to have. We're always going to have CO2 coming out of either human activity or industrial activity. Even if I replace 1 out of every 3 barrels of oil, there's still going to be CO2. So what can we do with the CO2 that comes out of that refinery? Well, you probably have heard about some of these, but there are ways to store it underground. There's a large interest in abiotic ways to just bury it, just like the country buried nuclear waste from the Manhattan Project. I've also talked about biological ways to bury it in promoting root development in crops and keeping it underground. We can convert that CO2 into fuels and chemicals. We can put traps in those refineries to use it and feed it to CO2 fixing microbes that would make fuels and chemicals. There's also a way to directly capture it and mineralize it and put it into products. So for example, one product that they're working on upstairs on the 2nd floor is to actually take the CO2 that comes from an industrial process and turn it into cement. There's normally carbonates put into cement to help it have the right tensile and strength properties and last. Those carbonates come from CO2 from petrochemical refining, but why not take it right out of the atmosphere at scale and recycle it into industrial processes? And you can look it up there. So with that, I'm just going to end. I think I'm a few minutes over, but hopefully I've been able to illustrate ways that we can decarbonize the Wisconsin idea. So we're big on the Wisconsin idea here, and that's doing things on campus that make a difference for the society. The chancellor's new tagline is to innovate for the public good. So I see decarbonizing the Wisconsin idea as a way to innovate for the public good. By doing this, we have the potential to lower greenhouse gas emissions, upcycle or make valuable products out of abundant raw materials, deliver products that are cost competitive. Society will not and probably should not pay 10 times more for one of our products than what they currently generate from what they pay for a fossil fuel product. And if it's done right, we can provide socioeconomic opportunity to underserved regions of the country that currently don't make money out of making these products. Let's make everybody a producer of these things instead of having an importer and producer economic situation. And we'll be able to expand a multi-trillion-dollar a year industry, at least in the United States and around the world even more. And by doing that, create over 1 billion jobs, according to government estimates. So with that, I've laid out a lot. We're not going to accomplish it all this semester, but I'll thank you for your attention and open the floor for questions. Thank you very much.
Thank you. So we do have a question online. Maybe I'll start with that as folks in the room are thinking about it. So Jenny asked about, I think maybe going back to that slide where you had the different, you had the map of the north central United States and where it's suitable to grow, especially crops. So her question was, how does creating biofuels from crops impact Native American reservations, given their majority of land is not able to grow crops? And also thinking about pipelines going through these lands, contaminating the land and water.
So we actually have active conversations with Native American groups on this issue who are very interested in what our technology could look like. They are, Jenny's right, they're not able to grow food crops, but they do grow biomass, native prairies. We've had people approach us about how to convert the lignocellulosic biomass in crops that grow on those acres into fuels and chemicals. And we actually have somebody in the building who's also an advisor, Grace Butel, who is very interested in how this activity would influence water quality, in particular on Native American lands. But that's a great question. Those are all things that we're thinking about, and I just didn't have a chance to go into them all. Thank you. Anything else? Yes.
Thank you so much for the talk. I was curious if you have thoughts on how a circular bioeconomy fits into an increasing need for products as well as energy products if we are changing land use, or we're going to also address.
So none of the land. So the question is, paraphrase it, how well does the circular bioeconomy play with society's need for food? And I'll just go back to the slides that I showed. None of those refineries were on productive food grade land. Last thing we want to do is use food grade land and turn it into fuel. We want to avoid what's called the food to fuel debate, right? Food versus fuel debate. So we think even on those productive lands where we're growing crops for food, we can take that lignocellulosic biomass and convert it into fuels and chemicals. We're not funded to work on those crops by DOE anymore, but it's just lignocellulose, and we could do that.
Thank you.
Yes, that's a great question. Yes, sir.
Yeah, so what would you put this technology for the biofuel in the TRL scale?
So where we are now, so the question is, where does this technology fit in a TRL scale? So to translate, TRL is a government funding or an industry funding term. T stands for technology, R stands for readiness, L stands for level. We are funded by DOE to do what I would call basic science. But if you look at what we do and put it on a TRL scale, it's probably 2, 3 to 4. TRL goes from 1 to 10, 9. That was close. I failed. So I got 90%. We have technologies that we have deployed that have moved into other parts of federal funding that are more translational or higher level TRL that are in the 6 to 7 or 8. So what I talked about is really early discovery science, 2 to 4.
So just the bio-based fuel side of it, because I know SAF and RNG are already being used.
RNG is deployed, so that's a much higher. What I talked about, making isobutanol at yields that we need out of biomass is TRL 2 to 4. There are planes that have flown on SAF, either 1 engine or 2 engines. You can decide if you want to get on a 2-engine plane and have both of them running on SAF or only one out of 2. Occasionally, not on a regular basis, because they're not being made at scale to supply. So there are technologies that have been scaled up, probably at the TRL 4 to 6 or 7 level, that produce molecules that have been commissioned by EPA and the aviation industry to use for sustainable aviation fuels. Yeah. Yes.
How long is like the research and like looking into the dairy industry waste products been a thing? Because I've actually never heard of that before. That sounds interesting.
That's all pretty new. They actually came to us about before everything is scaled by the pandemic, because I met with somebody in my office. They probably came to us about 4 years ago and said, we'd like you to make ethanol out of dairy residue. And I said, well, you don't want to make ethanol. There's an ethanol industry. You're going to be competing against a large industry. So we've been working with them and the people in the Center for Dairy Research over in Cal's to see what we can do to upgrade into other materials. If you go to that one paper that's there, you'll see probably half a dozen papers that we've published. That's really at the very beginning of what we need to do that. Yes.
So you mentioned the lack of need for fertilizers and the fact that the crops would ideally be perennials due to genome modification and stuff like that.
Well, there's native perennials.
Would there be
They're already doing it now. That's fine.
okay?
Yeah.
Would there be a fight against like the seed and fertilizers companies out there for this?
Yeah.
Yeah.
So agribusiness wants to continue to grow corn in all of those counties that are yellow on my map. I have no fight with that because I want to make, I don't want to prevent the production of food for people and for animals. In fact, 70% of the corn in the United States is used to feed animals, not to feed people. So we would need less corn if we all became vegetarians. That's a fact. I'm not promoting it. I like my steak, right? We don't have skin in that game. I'm not fighting with the agribusiness interest. In fact, I was just on a phone call on Friday with a major agribusiness company that has sites in Europe and around the world that wants to know more about what we're doing because they see what we're doing as the future. Around the world. So you look in the United States, I could think about it one way. Imagine if you were in Europe and your source of fossil fuels just dried up because of what's going on in Ukraine, right? Or imagine if you're in Africa and you want to provide materials for people there, right? So there's a large piece of this that's global. And I just showed some maps on the North Central region. We are funded by your taxpayer dollars and your parents' taxpayer dollars, so we worry about the United States.
My question for you guys.
All right.
I think
Anything
we're
else?
at time, so.
All right, well, maybe one more.
We're good.
It's just along the same lines. I was just wondering if we could then work with farmers and utilize like cash crop lands to just in the off seasons, especially in this area, planting, switchgrass and sorghum could be used as a cover crop. which would be better for regen ag.
We have been and continue to have conversations with farmers about these issues. Let me say the following about farmers, spoken as someone who was born and raised in New York City. Farmers are people. They have a heterogeneous set of opinions on what they should do. But farmers are also people because they worry about putting food on their table for their family, using land that they respect, because it's been, many of them, it's been passed down to them from their grandparents or great-grandparents, and because they like to use it for pleasure. They like to hunt, they like to fish, they like the beauty, they like birds. Having people, whether it's me or a farmer, change habits that they've had for decades, it's not going to be easy. Especially, to use your example, some of them will do it, but to use your example, you come into me and you say, you know, 20% of your acres is just not productive. And I think you should stop putting fertilizer and pesticide on it and grow energy crops. Okay. So tell me how that's going to work. And then you say, well, it's going to take you 5 years to get all the fertilizer out of the ground so that it can grow, and the pesticides out of the ground so you can grow perennials and produce them at yield that you're going to make money. I might show you the door. Unless there's an incentive from the government to have me do that. And we're not, then we have a whole policy conversation, what we do, right? But if you want to put food on the table, and I might buy into doing something with 20%, 30% of my land, but I'm not going to get any profits out of that acreage for 5 years. Even if I trust you, I might not do it. But I might not trust you because that agribusiness guy or gal has been in my kitchen every year selling me products and I'm feeding my family, right? So it's a nuanced situation. And nobody's right, nobody's wrong. But those are the facts. Because I can tell you, we studied this. It's going to take 3 to 5 years to take that so-called non-productive land, switch it to another crop. Or even put cover crops in, because cover crops won't go because of the residual pesticides from the last 50 years that have been put on that land, right? For a while. Thank you.
Thanks so much.
Thanks again.